Hey, hello, workshop students. As you're getting ready here, studying for the final, again, got a couple of questions. Let's do my second one here on this list. Number 7. And so number 7, let's read it here together. It says block number 1, and they give us a mass, and block number 2, and they give us a mass, are side by side on a frictionless table. All right, so I'm going to draw a table. I'm going to put them side by side. It looks like the first one said 3.8 kilograms, and the second one is 1.40 kilograms. I'll call it M1 and M2. Okay, so block 1, block 2, side by side on a frictionless table. A person pushes horizontally on block number 1 with a force of 10 newtons. All right, so maybe I'll just kind of put a little arrowhead, say 10 newtons. That's kind of be my free body diagram. I guess technically my free body diagram should include gravity pulling down and normal force pushing up. But I have a feeling this is a horizontal related problem, and so I really probably don't need to worry about the forces up and down. I should point out there is no friction, so I don't have to do that horizontal force, but there is a force of number 1 pushing on number 2. Let me just do an arrow back and forth, and then Newton's third law saying number 2 is pushing back on number 1. So let me keep reading the problem here, but that diagram has gotten pretty messy now, and I probably need to clean it up a little bit. But let's see. A person pushes horizontally with a force of 10 newtons and causes both blocks to accelerate. During this push, block 1, there we go, pushes on number 2 with a force of. So they're asking for that force. So I'm going to do a free body diagram. And actually, I am going to do 3 free body diagrams, although I kind of suspect I will not need all 3. But for completeness of your education, maybe I should. So the first 2 I'll call them my obvious free body diagrams. They are just take block number 1 and say what forces are in block number 1. And so block number 1 is being pushed with a force of 10 newtons. Let me not draw the gravitational or the normal, as I said earlier. Let me just focus on the horizontal ones. And then this is a key step that I mentioned here. Block 1 needs to push on block number 2. So the third law says block number 2, and so maybe I'll just call this F number 2, is pushing back on block number 1. Okay. Now, notice then that if I do a free body diagram of block number 2, I would see that block number 2 is being pushed, and it is from number 1. It's this little contact area between them, and it's kind of important to keep track of our forces, which ones are which, but just as important is to realize block number 2 does move. Block number 2 does have a force on it, but this person pushing is not putting a force on number 2. This person pushing puts it on number 1, and then the contact surface between 1 and 2 is where number 2 gets a force. And of course, then 2 pushes back on number 1. And again, I'm going to say the same thing. Let me not do the vertical forces here. This is just kind of a horizontal problem here. Now, another free body diagram might be to view the 2 collectively as one big object. And so its mass would be M1 plus M2. And it's being pushed with a force of 10 newtons. And there is nothing pushing back. Now, I know 1 pushes on 2, but 2 pushes back on 1. And so this is what we've referred to as internal forces. And since they're always equal and opposite, we don't add them together when we are trying to say figure out the net force by adding up all the forces and setting it equal to mass times acceleration. And we never worry about the internal forces. If we had to, that would be a mess. We'd have to, say, well, this atom is connected to this atom, which is connected to that atom, and is connected to that atom, and we'd have to worry about all those internal ones. And fortunately, we don't. And so when we say add up all the forces, we really mean add up all the external forces, because we know all the internal ones go to zero. And so this is why this one can become probably a useful problem. I can't do it by itself, because ultimately I've got to do this picture or this picture, because I've got to find force number 2, and each of these have force number 2. But this one doesn't have force number 2 and can tell me something about the whole acceleration. So just kind of setting up my free body diagram and realizing internal forces don't come into play, this is my go-to for this one, but it's also my insight of why I got to separate them, because if you have them hooked up collectively, since internal forces don't do anything, they don't cancel out, they won't become part of your equation, and you can't solve for what they're asking for. So this free body diagram will not allow us to completely get to our answer. And in fact, maybe I will just look at the second free body diagram and apply Newton's second law, because if I add up all the horizontal forces, it's just F number 2, what we're looking for, and that would equal mass number 2 times the acceleration of number 2. And of course, we do know mass number 2 as 1.4, but we don't know the acceleration, and therefore we don't really, by itself, we're not able to get this force number 2. So we need another equation, which then means we could do either this one or this one, but we don't need to do both. And it's kind of your call. I kind of am inviting by this one, but that's what I said earlier, that I think I probably will need 2 of these free body diagrams. And any 2 would work, really. So anyways, I'm a little more invited by this one, because when I add up all these forces, so when I take Newton's second law, this is the only one, it's 10 newtons. And that has to equal mass times acceleration. But here the mass is, I'm thinking of them as collectively the 2 together. So if I take, let's see, 3 and 1 makes 4, and that's 5.2. So together, this is 5.2 kilograms times A. And this will allow me to get A, which, by the way, that one too would. It would just be a little bit harder mathematics. So if I grab my calculator here and take the 10 and divide it by the 5.2, I get an acceleration of 1.92, which now, if I use this up here, I can now get what this question is after, which is force number 2. So that number times 1.4, giving me about 2.69. 2.69. Good. And hopefully, yeah, that's what the computer said was the correct answer. All right. Hope that one helps.